reverse engineering stuff. Maybe 5 or 6 of those. There will be a take-home midterm and then a final project. Anyone may select their final project at any point in time and begin working on it. And actually, I'm just going to make this offer. If you write an O day or an N day that works on a live system, which is an exploit for a bug no one knows about, or an exploit for a bug that exists but has not been exploited in the wild by anybody publicly, that's an A. That's an A for the whole class. You do that for your final project, you get an A. I don't care what else you do. Here's why. Because that's all that matters in real life. And all of this is to get you to do that. If you can do that, that's it. No one else will care what else you do. I actually had my sister-in-law is a VP for an IT group in a really stressed out cloud company. And we were at dinner and she said, "Damn security people get away with everything." And I didn't say anything, I smiled. But in my head, my brain was like, you done got colonized. The reason the security people get away with anything is because they don't put up with BS, right? They know they could just go and own stuff. And my view is always, if you want to fire me, fire me. Fire me right now, I'll be happy. Get some severance, I'll go drop products, no problem. If you find a good O day for a final project, it's probably an 8. Straight up. Straight up. The rest of this is getting you comfortable with doing the hard thing, which is learning unfamiliar architectures, unfamiliar programs, unfamiliar operating systems, and exercising the muscle of learning. So I am 42, I'll be 43 next month, and I am now starting to transfer all my Windows kernel knowledge to Linux kernel knowledge, and that means like I get a day off on Saturday, so I'm just going to sit down and start work, and I'll do 8 hours of work on my own, right? Somebody else here who's not here right now, so let me just call him out, said, I want to get my ass kicked, right? And the problem is no one's going to kick your ass, you have to kick your own ass. And the more you kick your own ass, the sooner, the easier you get at kicking your own ass, and the less resistance there is. It's a muscle like everything else, right? I heard a really cool concept the other day, which was anarchist calisthenics. And the idea is, when it doesn't matter and the stakes are really low, break rules, so that when it does matter and the stakes are really high, you have the courage and the ability to break rules. Right? And it's the same thing with learning this stuff and doing this work. Right now you are young and you theoretically don't have children or houses or farm animals or all this other garbage that you need to upkeep. And so you can start doing that grind. The more you do it now, the harder you do it now, the easier it is later on when stuff actually gets tough. Today, I'm going to give kind of a context lecture. So I've been kicking your butts pretty hard up until this point. Every class has had a lot of assembly in it, a lot of debugger in it, a lot of like, this is how stuff works. This class, we're going to take it easy a little bit, and I'm going to give a context talk. A lot of people have asked, how do I do this technique? How do I do that technique? And when I started to answer that, I've got back answers from people that are like, well, they don't understand. So they understand the solution, but they don't understand the problem the solution solves fully. And the problem the solution solves always needs to be the first thing in your mind. You are always solving a problem. You are never doing math in the abstract, right? This is a problem that white hats have. If you are not solving a problem, how do you know what to do? How do you know when you won? How do you know where to go? I had some younger researcher come up to me at Black Hat a couple years ago and say, what should I research next? And I was like, what can't you break into? And she looked at me like I had 3 heads, right? Like, if you're not trying to break into something, you'll have no idea what to research, nor will you know when that research was useful to anybody, nor will you know if it fits into the real world, right? Like, engineers just don't go engineering stuff that doesn't solve a problem. You are engineers in this, right? You are engineering the solution to a problem, the simplest, most reliable solution to a problem. So this talk kind of goes through the history of kind of public exploitation in the back and forth arms race between people writing exploits and breaking into computers, and the way that industry responded to that in terms of mitigations. And then what after the mitigation, what happens to become the next lowest fence to hop, right? And so you're just pushing each other back and forth. What's the easiest thing for you to do to stop me? What's the easiest thing for me to do to break in again afterwards, right? And so this is broken down kind of back and forth steps, right? Orange, white, orange, white, orange, white. This is not the entire history. There's going to be a lot of stuff that I skip here, but it's going to cover the majority of mitigations that you will have to bypass in modern life, right? So there's no format string bugs in here. Format string bugs were kind of interesting for a little while, but they're very specific, right? They existed for a little while, and then compilers basically made them extinct. The only time you're going to see them is in some embedded hardware, and if you do see them, basically you just get a free write rollware. And it's not difficult, right? So we could sit down and walk through a billion of the examples, but if you can do the homework, you can hit a format string bug, right? That's all there is to it. So these are the things that I left out. We already talked base pointer overwrites. And we talked a little stack pointing. Double frees are a form of use after free, and we will talk about that. These, no one has mitigated yet, and I will teach you them in the second portion of class. This is where you get things. This is something that is needed for actually performing these attacks, and so it's a skill that you'll learn. Yeah. All right, you've done this already, right? You did this in the first lab, you did this in the homework. Everybody should recognize kind of that diagram and how it works and what you're hitting, right? The other thing that you have seen in the homework is a stack cookie or a stack canary. That is a value that is placed usually between the local variables and the old EVP, so immediately before, immediately after EVP. Sometimes EVP is here, sometimes EVP is here, and usually it's here, but that's compiler specific, right?
So I saw on one of the topics you said you omitted was a stack canary. So what's the difference between a cookie and a canary?
That's my mistake, I didn't it. I'm also not taking audio on this. All right, so we're starting the audio on the stack. Okay, so this came out kind of in Linux and Windows, kind of at a similar period in time. On Linux, it was called Propolis when it was first released, and it came out with another set of page protections. But you've seen this. You saw my implementation of it. Generally, the way this works is, in that start symbol, before main gets called, another cookie initialization function is called. That one is going to make a random number, and it's going to stick it in a global variable somewhere that you don't get to look at as an attacker. And then at the end, right before the ret, usually in line, there's another function call that just checks it. It says, if this cookie is not equal to the random variable on this in global space, probably in .data, then throw an exception. Okay. Here's the first big mistake they made is, if they're not the same, throw an exception. Now, you've also seen great ways to bypass this, but there is a couple other problems here. The first one is that you still have access to these local variables even without touching the cookie, right? And so in a situation where the compiler has not reordered the stack, and some modern compilers will reorder the stack, that's one of the things they turn off in the makefile, right? In that case, all local buffers that are not arrays are placed below all buffers that are arrays. Now that's not foolproof, right? You can overflow from one array into another array, and if it's a set of structures, there's still a lot of great stuff there. Sometimes there's a bunch of function pointers there, right? Any class will often have virtual function pointers in it. If you were in the grad seminar last time, we talked about vtables. That's an example, right? And then there's certain copy loops that will allow you to bypass it and write up the stack. There is a bug that I did very recently on a satellite, and the way it worked was it actually had kind of a very small web browser, or not web browser, web server. And when it would read the headers, anytime it saw /r/n, it would hop up to the next string that it had. So it had an array of fixed length strings. Every RN would walk it up. So if you put in too many RNs, it would just walk up the stack, and you could walk right over the cookie and then hit some other stack frame, right? Okay, so here's an example of our ordering. In this case, our stack cookie has been placed between our stack variables and our local primitives. Sometimes you will see that, and sometimes you will see the cookie still here, but the reordering has occurred where these locals are underneath the buffer. And that's going to be compiler specific, compiler dependent. All right. So on Windows, the way people generally got around this was you would have, this is cut off, that's actually in E, structured exception handler. And the way that exception handling works in C++ on both Windows and Linux is that if you think about how you write nested code with exception handlers with try except blocks, right? What will happen is as the code is running through the stack, when you run a function that has an except block or try except, it will put a data structure on the top of the stack there. And that data structure works as a linked list. So you have a top level exception handler, right? And then every nested one underneath is a part of the linked list, a backwards linked list to it. So if you throw an exception 3 functions in, it'll try that exception handler and it'll say, what do you catch, right? When you set an exception block, you can say, catch these types of exceptions, right? You're not supposed to do a wildcard exception handler. Please don't ever do a wildcard exception handler. If you are a black hat, the best gift any programmer can give you is a wildcard exception handler, right? Because now you've corrupted all the memory, and you will definitely continue to run. And the user won't know, and the programmer won't know when they're testing. Do not do it unless you want to be kind to your fellow students, in which case do it. But what happens is it'll check to see if the most recent exception handler on the stack can handle the exception. If not, it'll walk up the next pointer in linked list further up the stack to the next one and check that to see, and it'll walk all the way up the chain to the top. Okay, but these are on the stack. So if you blow right on through this and screw everything up to here, to your handler, right? And then this is your return address, basically, in this case, right? It will walk up and say, oh, this is structured exception handler catches that cookie exception, run the handler, right? Your except block is just a function pointer to a function that gets called. That's how that gets put together, right? Your try block is the normal function. Your except block is a handler. It gets pulled out to another function, and it gets set as part of this structure, okay? So part of our linked list, it goes up to the next exception handler, the actual function. And so in this case, the way that you can exploit this is very simple, right? You can set this to a pop rec or a jump ESP and put your shellcode right after it, just like you did with Lab 1. And you have a generic solution to beating the stack cookie on Windows, okay? Okay, but that's a generic solution, and we are attacking the way that the compiler builds things. And when we are attacking something the compiler does, or kind of a boilerplate solution, or something that the libraries do habitually, that means that there is a single place where it can be mitigated, right? I can make a change to the compiler to protect that exception handler, and then validate the chain before I run it. So what they end up doing is the same thing that they do to beat our heap unlinks that we'll talk about later is they validate the chain. How do you validate the chain? Before you run the handler, you walk the next pointer, you walk it all the way up to the top of the chain, and you say, if I don't reach my top level exception handler, which I've stored off someplace else, then the chain is broken, right? Someone has busted up this pointer right here. Now, if you know the address of the top level handler, game on. You just put that address there, provided it's not got zeros in it or something, and you're good to go, right? But you have to know. So when you are thinking about exploiting things, there are several pieces that you keep in your head. It's what can I write? What can I read? What do I know? And what do I not know? And what do I know usually means, can I find out where something is in memory that I need, right? If you know in memory where the stack cookie is, the global stack cookie, and you have an info disclosure bug, something that lets you dump memory arbitrarily, then you could dump out the stack cookie, right? But you'd have to be able to do that before you hit the stack cookie. It will not change in the program. That thing gets, that random number gets set during the start, and it doesn't change. For the whole program, it's all the same. Different programs will be different. It gets randomized at start time. But if you have two bugs, and one is an arbitrary read and one's an arbitrary write, game on, you're good to go, right? And that's what kind of ASLR plays upon. When we get there, we'll see that what's going on is that they are saying the things that you relied upon, for instance, the address of gadgets, we're going to make that move. Every time the program runs, it's going to be in a different place, right? So now what you know is different, right? You need to get something else to make that whole chain work. Once they made that structured exception handler fix, it became easier to hit the heap than the stack, okay? And people kind of understood that they shouldn't write stack overflows. It took like 70 years of computing for people to figure out that they shouldn't write stack overflows. And it didn't occur to them they should think about it really until the internet got big enough that any 14-year-old could take over your server, because writing those stack-based buffer overflows when there's no mitigations is not actually that difficult, right? You can imagine being 14-year-old and doing that. And at the time, anytime before 2003, any 14-year-old on Earth could have a great time popping any server on Earth, right? And you could do it by yourself in your room or with two of your friends. Okay? It was harder to find the bug than it was to own it. After 2003, you start to see people hitting heap overflows, okay? There was no reason to do something as complicated as hitting the heap until it became difficult to hit the stack. And for a while, people didn't think this was doable. Like, they thought it was not possible, right? I don't know if anybody looks at like sporting events where times or scores or doing tricks is important, but you will always see that people will say something is impossible until one person does it, and then 15 other people do it immediately afterwards, right? It is about what you think is possible and what you don't think is possible and what's worthwhile to do. If no one else is doing it, you don't have to do it either. So this is a representation of the first types of heaps that we are going to cover. I refer to these as DL Malik heaps. They're named after a guy named Doug Lee, DL. And those are heaps where the metadata for each heap chunk is stored inline. That means Here's the data. When you call malloc, you get a pointer right here. You write all of this with your code. This lives immediately prior to that pointer. So if you took a pointer in C that you called malloc on, and you say pointer -8, you can look at these values. You can do it in the debugger also, right? And what you have is two linked lists that sit on top of each other. The first linked list is a linked list of all of the memory in the page, and the second linked list is a linked list of just the chunks that are free. One of the big problems of this type of heap, we'll get into it very deeply in the second portion of class, is fragmentation. And so part of what this heap needs to do is anytime something is freed, it will defragment itself, basically. It'll say, is this free chunk next to another free chunk? If so, instead of having two right next to each other, make it one big one in case somebody needs something of that size, okay? And so what's happening here is, if you have an overflow, you can overflow into the next chunk's linked list and control these guys and then get an unlinked bug. We'll talk about exactly how unlinked bugs work later, but what you see is two things happening. The first is people realize, shoot, we shouldn't have put the metadata right next to the data. Two, we're going to have to validate all that data just like we did with the structured exception handlers. And then three, well, it's not that big a deal because it's so non-deterministic, right? When, let's say you were attacking a web server, the stack is always going to be in the same place relative to the function that's called, right? It's static. You know, if you get a write somewhere on the stack, you know exactly what the rest of the stack looks like because you know what the call chain looks like, right? So all the way up, it's always going to be the same every time. If there's a function pointer, your previous frame will be different, but your frame will always be the same, right? In the heap case, how many people are using the web server right now? How much memory each of those people is using? All of that stuff matters. How long has the web server been running? That's going to dictate what the heap looks like. And you, as a remote attacker, have no idea when you came into this situation. The web server could have just been started, in which case it's clean. It could have been running for, I have an uptime of 400 days, right? It's going to be filthy. It's going to be filthy. There's going to be a lot of probably memory leaks where people have allocated things that they have then lost pointers to, and it's just living, breaking up the heap. But in 2007, a man named Alex Todorov came up with a technique to turn a non-deterministic chaotic system into a predictable system. And it's actually incredibly simple. And he called it heap feng shui. Sometimes people call it heap grooming. You are basically just paving over, right? If you allocate enough stuff of the right sizes, you will fill all of the space. And once you have filled all of the empty space, the operating system will start to allocate clean pages. And once it starts allocating clean pages, then you have clean pages to work with and make deterministic in your own way. So first step is pave over it, and then the second step is set it up in such a way that you can be sure, or at least sure within 90% probability on a certain amount of RAM with a certain number of processors and an average user load that you can guess, that you will hit something that you want to hit and not something somebody else has made. Okay? So in this case, for DL malloc, it's incredibly chaotic. Okay? The newer version for libc is PT malloc, pthread, and that is Doug Lee's malloc, except each thread has its own look-aside lists. We'll talk about what those are when we get to the heap. But basically what it means is, rather than having every thread thrashing the whole thing, we split it up somewhat so each thread kind of has its own heap, right? There can be multiple heaps, okay? And when you get into more complex systems, web browsers in particular, you will see that those heaps are split out. We'll talk about that later. But with that kind of realization and Alex's technique, it meant that you could make heap bugs really, really reliable. It used to be like, oh, I'll write this exploit and then I'll run it 256 times in a row, and maybe one of them will hit. And because it's going to be a nifty is running, whatever is running the service is just restarting the service every time it crashes. Now you've filled the log with, oh, I've crashed the server 256 times, which eventually you get a shell and most people aren't looking at the log, and it's just kind of a dirty way to do it, right? But it was doable. After that, you could get your heap exploits even on situations like this in the high 90 percentile, right? And so that was one thing that you would do if you were selling this bug to somebody. Part of the documentation you would provide them is, under this load, on this server, with this version of libc, I had 500,000 bots thrashing the server, and then I ran the exploit 100,000 times. And of 100,000 times I ran the exploit, I gained a 96.3% success rate. And so if you were going to hand that to an operator, they could look at that and be like, well, I have a 96.3% chance of not getting shot or burning this bug or something like that, right? This is the least optimized heap, and you can get it there. So here's how that unlinking bug kind of works. And all the grad students will see this. This is why I gave you this example. Does anybody recognize what that code does? Is that, Stefan, is that you in the back? I can't see. Yeah, what does it do?
It's checking that whatever P is, it's checking that P's next previous pointer also points back to P itself.
No, it is not validating the chain. Like there's only one equal sign.
Does it delete the entry?
It removes, it's just a doubly linked list delete, right? It removes a node from a doubly linked list. Right, it says next prev, p next prev is now going to be equal to p prev. So my previous is now here, and then p prev next is going to be equal to my next. Right, so it reroutes, and then you can free p from the middle. Right, so it is referenced by the doubly linked list element that's being pulled out, and it's kind of rerouting those. Now the funny thing is if you have control of these, you have control of next and previous, right? And so what you basically get there is a write what where, right? You can do exactly what you do in the first homework, which is you can write an arbitrary 4 bytes to an arbitrary location. And there are some restrictions on that. Chiefly among them is that the 4 bytes after where you wrote are going to be written to, because it's going to be writing the next and the prev. So those 4 bytes need to be writable. And then if you're going to put your shellcode there, well, that's going to be garbage now. So you had better make sure that the very first 4 bytes are a relative hop forward 6 bytes or whatever, right? So what do they do to solve this problem? They do the exact same thing that they do with the structured exception handler chain, which is every time you consolidate 2 free chunks together, you walk the entire list, right? Now, how expensive is that? In big O.
Oh, then you're walking the entire list?
It's O of n plus n over 2 on average, right? Because so normally the unlink itself for a singly linked list is going to be half time average, but every time you do it, you're going to walk the whole list again. Every time you do this consolidation, right? So yeah, you're basically more than doubling the time to consolidate these chunks together. And so you might imagine that on some operating systems, on some embedded devices, it's not worth it, right? Because you might be thrashing the heap quite a lot on any given device. And so Is it really worth it to spend all that time and slow down whatever your embedded device is to do that? And often the answer is no. Right? All of these things are a trade-off. If you looked at optimization in general, you can generally trade memory footprint for processor speed or processor speed for memory footprint, right? The same trade-offs occur when you are looking at validation. You can trade memory footprint for security. You can trade processor thrash for security. I should have looked at my slides so I knew what to hit the button. All right. So once people decided that was still a problem, one way is to validate the whole heap every time. The other way to solve this problem is to take all the metadata, and instead of putting it in line with your heap chunks, you pull it out to its own page. And that page is non-contiguous with the rest of the heap. Like there's a guard page in between, a page that is neither read, write, or executable, so you can't write into it from anywhere. And then you put all the metadata there. Now this means that you have a lot less defragmentation to do on your heap, but it also takes up more memory space in general. And there are actually inflection points for which one or the other style of heap is more efficient. And so on Windows, generally you will start with the other type of heap, with a DL-malloc type of heap. And then once the program's performance counters hit a certain threshold, they'll switch to a different type of heap. And that is the low fragmentation heap, which is of this type, where the metadata is not inline. And on Linux or Android, that is JL-malloc, right? JE-malloc. DL-malloc, JE-malloc. So JE-malloc and low fragmentation heap are the exact same thing. They are non-inline metadata heaps, okay? So now, you can't hit the metadata and do an unlink attack. However, nobody can validate the data anymore either. If we're using the other kind of heap, if you're using this kind of heap, you can validate the chain. You can say someone corrupted this, right? However, if you're using this kind of heap, the library cannot validate the chain anymore. So the library and the compiler can no longer say, I've noticed that somebody corrupted heap memory. Okay, so now it's on the programmer. And how many of you validate all of your chains? Did I lose my sound? I did. I was wondering if anybody ever charged this thing. Well, I'll have to yell more. Yeah, so now you are in a situation where in some cases, things are dangerous because you have access to data you shouldn't, and in some cases, things are dangerous because there's no way the program can tell, right? Like, if you have written code in your life, do you validate that everything you wrote is still what you thought it was, which requires you to store things twice? Has anybody ever done that? No. Has anybody ever written a linked list in a program? Do you walk the whole linked list every time you use it to see if it's correct or not? No, right? Nobody does. The only time that happens is in boilerplate library code, because the library developer can save you from yourself in some situations. But the regular developer calling the library never does and never can. Okay? So, what is the difference for you as a black hat between attacking the other type of heap and doing an unlink, or any of the techniques? So if anybody's read or is familiar with Maleficarum, which is a FRAC article from 2000, a long-ass time ago, which I suggest you read, that is specifically attacking the library, right? The allocator is not part of the operating system. It's part of libc. You can compile in your own allocator. In one of the labs, I specifically compile in malloc on purpose so that you get a chance to mess with it, right? Even though it's not the default for the operating system, you can say, if you're building the program, use this heap instead. It's part of the library, not even part of the operating system, right? The operating system hands you pages. Every time you call brk or ntallocate memory, you get a page, 4096 bytes. And then what the library does with that is whatever it wants. And it provides you malloc and free so that you're not working with raw pages and you don't have to do it yourself, but it's the library that's doing it. So in the other case, what you have to know is how the library works. And often that does not change for very long periods of time, like a decade, right? Until somebody makes another mitigation or decides that the way that we are doing this is not as efficient as it could be under the current load conditions of the type of programs people want to run. One time you might see this in your lifetime is cloud allocators. The most expensive part of cloud computing is that the allocator gets called over and over and over and over and over and over again. And so there are optimizations you can make to save a lot of cloud money by making that as light as possible or putting in your own custom allocator, right? So that will be a time that's something that I expect to see in the future, and you should probably learn those heaps and own them, so I don't have to. But what you are learning is a generic solution. All of the malloc maleficarum generic solution for the library. What you should be doing is every time you own something on the heap, own the program. This means you need to do a lot more reverse engineering to understand what's going on in the program, to know what you can attack in the program, rather than having this generic boilerplate solution. Side note. At each one of these steps in this chain of back and forth, many people fall off. And what I mean by that is everybody that learned generic solutions and thought hacking was this set of 4 generic solutions, when they got to the next step, they could not figure out how to own stuff anymore, or it became too hard, or they decided they were done learning the next generic solution. If you don't think in generic solutions, but you think in what I can read, what I can write, what I know, and what I need to know to solve this puzzle, you will not fall off. But I remember many, many people who thought they were hot stuff at Stack Overflows. When the stack became too hard and people needed to hit the heap, they couldn't do it anymore. They got different jobs. Okay? So let's look a little bit closer about how Alex made everybody upset. So, let's see how I lay this out. Yeah, okay. So the technique is you pave it over. That means you allocate things, you allocate a certain amount of certain sizes. Now, a lot of more modern heaps have a couple optimizations in there that you can learn about where they'll have what's called look-aside lists. Stop it.
Oh no.
I'll remember this. Never send bugs. Don't send bugs. That's working for free. Those are yours. You keep them for yourself. Okay, so the first thing you do is pave it over, and that means you've got a set of look-aside lists that kind of optimize this solution, right? And I'll talk about those when we get specifically into heaps. But know that there are power of 2 singly linked lists that make it very easy for the library, instead of walking the whole W-linked list looking for a free size it wants, it's got this other list that stores the same data, but it's stored by power of 2 size. So it can say, oh, I need a 16 byte chunk. Just pull the first one off the list, and now the root node for the 16 byte list is whatever net.next, right? So it's very fast, and so you allocate a certain amount of each of those buckets, and that amount is going to be however big the list is for that operating system for that library, right? Targeting is very important. You need to know what you're trying to hit. And that will clear out the look-aside list. And then, based on how much memory you assume this server has, which you can calculate, and you can calculate it because IT people can calculate it, and IT people can calculate it because there's money involved and they have to. And so they'll say the number of users, the number of servers, I need this much RAM in the servers, I justify that cost, etc. All these things are benefit analysis. So you can do the same thing. Anything that the IT people who built it or the engineers who built it can do, you can do. You can see all their code. That's why security programs don't work, because you can buy them. No one can trick you. You just test your exploit with all of them. You buy them, and you install them, and you test them, and once you beat them, then you send it out. Don't run it before you tested it. Okay, so you filled that. What's the next step? The next step is you allocate a whole bunch of stuff of the size of the object that you have an overflow in. So let's say I have a 30 hex byte object that has my bug in it that's going to do the overflow. I allocate a ton of those. And then I free every other one. And so now I've got control of these, so I've got references to them, and I've got a bunch of holes. And the probability is, depending on how many holes I've made, the next thing I allocate in that size is going to go in one of those holes, right? And so in this case, we filled this hole in, and we do our overflow, and we hit this one, right? So this is the one that's been corrupted. And once I do that, I call the function pointers in each one of them, boom, all the way down the list. For all the ones I didn't hit, they're going to return just fine. Call it, return nothing. Call it, return nothing. Call it, now my shellcode gets run. Right? And so if you want to have more probability of getting it right, you just make more holes. Right? That's all. However, there was something that you had to know, and that is your vtable, which is how C++ class objects store their function pointers, has one level of indirection in it. Right? So this vtable pointer points to an array on the code pages, which is not writable, and that's just an array of function pointers. So 2, FN1. This is part of the object. That points here. This is not writable. This is writable. And then this points at the code, which is not writable, but it is executable. Not writable. Yes, executable. So you can't just point this vtable at code. You have to point it at something that points at code. And so you have to know where there is some place that you could point to point at code. Now, this could be pointed at any data you want. It's not validated, so you can point it to another heap object. You could point it into yourself. You could point it onto the stack, but you have to know where those things are. This is something you have to know, right? However, before page protections were what they are now, you could pull a sweet little trick. And that sweet little trick was, you could pick an address that could be misaligned so that the whole address is the same byte. So it doesn't matter where I align it. The classic one picked was OC, 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 and this has a couple properties. If you fill all the memory space in a browser with this, here's what happens. It doesn't matter if I have I'll say I have thousands and thousands of bytes of OC, 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 and then I have my shellcode right after. This is a self-referential pointer that can be misaligned, that is also a not. So if I overwrite this vtable with OC, 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 and then I jump to OC, 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 and then all that's there is OC, 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 And then my shell code, in this case I'm drawing it backwards because I'm an idiot, but you just start executing these nops, boom, 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 and then you hit your shell code, right? So there's a generic solution to this problem at the time, and that was somewhat reliant on you being able to allocate however much you wanted, but it worked real well.
So is that just like a part of like the instruction set where like when the processor tries to access that bit of memory, it'll just return whatever is at that location? Like, how's it self-referential?
It's self-referential in that if you filled up enough memory, you would fill up the address OC, 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 OC.
Oh, okay.
Right, so I'm flooding the whole thing with these OCs, and eventually I would get this page allocated on the heap, right? So it's not self-referential except in that I could cause it to be allocated.
Oh, okay.
Okay, and it happens to be an address I can cause to be allocated that is also a NOP, and I'm using the property of every byte is the same, so I can't be misaligned on my pointer. I could be off by 1, I could be off by 3, I could be off by 2, I could be off by 4. It's always going to be OC, 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 right? This trick no longer works, but if you're doing embedded stuff, it probably does. And it's probably really easy to get addresses like that allocated too, because there's not going to be much memory on the system, right? Probably won't be OC, 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 but you can find something else like it, where you can say, okay, the top 2 bytes of the page are the same and also a NOP, and I can cause them to be allocated. That would be the criteria you would need to satisfy. Does that make sense? Because if you can get those top 2 bytes allocated, you can set the bottom 2 bytes, right? Those pages are what you're getting allocated, it's the bottom 2, okay? So it might not be OC, 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 but that technique will still work on probably just a ton of embedded devices. Probably work on older Android phones, right? There are a lot of Android phones out there, and there will be till the end of time, that are low-budget burner phones or used in other countries where the budgets are lower. And all these techniques are still going to work on those. We're using the older stuff. Okay, so there are many other options that are specific to your library that still work, that can't be validated. One of the qualities of a doubly linked list is that you can validate it back and forth. A singly linked list, unless you are going towards a known value, like something at the top, can't be validated. Or the thing that the linked list is for, which is speed in this case, would be kind of negated if you were to validate it every single time. So it's not worth it. Why would you add these look-aside lists if you're also going to validate them? You just lost the benefit entirely, right? So here's kind of like a visual representation of a set of look-aside lists. So let's say X is probably going to be 8. That's going to be your minimum allocation. It doesn't matter how much memory you ask for. If it's smaller than 8, you're going to get 8. And the reason is because the metadata takes up 8. And so if you ask for less than 8, it would be just silly for the computer to give you that much, right? So, and then generally it'll go in powers of 2 from there. So 8, 16, 32, et cetera, up to a certain amount. Okay. If you can cause an arbitrary address to get freed, let's say you overwrite a pointer and that pointer is freed, right? And the metadata says it's of a certain size, like a size that has space on the look-aside list, that pointer you freed will go into the look-aside list. And it may not be a heap pointer, or it may be somebody else's heap pointer. And what you would do in that case is ask for that size to be allocated, and you will be handed back that pointer, and then the code will write to it. So this is another way to get a write what where, right? I free an arbitrary pointer. I ask the program to allocate that size that I told it was. Doesn't have to be the same size. If I'm writing over the metadata, I get it back. Now my program thinks that that's my data, that's my memory to write to, even if it's somebody else's. I write what I want there, and now I've overwritten that arbitrary pointer, right?
Just coming back, these look-aside lists aren't process dependent.
Processed. Yeah, they are.
They're like process.
Yeah. So you came in late.
I did. I got stuck.
What I said earlier is all heaps are controlled by the library themselves. They're per process, right? When the kernel gives you memory, it gives it to you in a page, and then what your program does with that page is up to it.
I got. You said it might belong to a different user, but you mean like a different user?
I'm sorry, a different. A different thread. Somebody else's code, right? Yeah. Sorry, I was imprecise. You're correct.
No, that's okay.
This is not the best way to do this, right? Because somebody could beat you to it. In the other way that we looked at where you're making those holes, nobody can beat you to it. Somebody might fill in some of the holes, but as long as you get into one of them, you're fine. Nobody else is doing overwriting. So it doesn't matter if you're calling those function pointers, they're just going to work until you get to the one that you wrote, which is wrong. But if somebody beats you to this and pulls this off again, they're going to write data to that arbitrary pointer. And if they do that, the program's likely to crash because they're not looking to make it work, right? And when I say they, I mean some other part of the code that is not the part of the code that you are concerned with in the moment. That's basically what I mean, right? Like if we have two threads running and I am one of the users, it's a web server, my thread handles my inputs. You've got another user, they have their own thread. They're still sharing the same heap. They might pull that off earlier. Or even if it's in my thread, side effects of what I'm doing may cause allocations to happen. And this is a problem that you'll get into quite a lot if you're looking at more complex heap problems where you'll say, well, I sent this data in order to get this thing allocated, but when I sent the data, because it was the size of the thing that needed to be allocated, the program allocated another chunk of the same size. So now I have to make sure that I'm the second thing on the look-aside list so that when it pulls its chunk off, that is not the one that I wanted, so the second one that comes out is mine. So that means after I put this on, I have to free something else of the same size, so I move it over. Like, that's the sort of stuff that you get into when you're messing with heaps, right? And this is why people were like, we don't want to do this until it became kind of necessary, right? One of the mitigations that you can see on this, and you will almost never see, is pointer XORing, which is kind of like a stat canary where the program will make a random number, and then every pointer that it puts into a linked list and pulls out again, it'll XOR by that number. It's a lot quicker, but it means that you can't write directly to it, right? Except using the proper mechanisms that perform that XOR back and forth, right? So that's one way that you could protect pointers. It's a lot faster than chain validation. So this is kind of showing the way that I don't like to do stack overflows, which is returning back into the stack and hitting your NOP sled and kind of running into your shellcode. And we went directly past this into the proper way to do it, which is returning into a library. Okay, so there's actually a mitigation that stops you from returning into the heap, and that is known as DEP, or when it was first introduced in Linux, right around the time of the canary, it was W XOR X, which meant write XOR execute. If it was executable, it wasn't writable. If it's writable, it wasn't executable. Right? That was the way that pages got mapped. And so it meant you could not return back into the stack or into the heap or into any of the other pages that weren't supposed to have code in them, except for the code page or the text segment, right? And so this is broken by any JIT, obviously, but at the time there was no JITting. So it was more about making sure that the page protections were exactly what they needed to be. And for this to be possible, they had to update all of the processors, right? At the time in the 90s, there was no way to set enough flags to have it be write XOR execute. They had to add that to the hardware. And the reason was the more flags you add to a code page table, the larger the code page table gets. And that code page table is getting hit constantly. Every time somebody looks up memory, that code page table is getting hit. And the larger you make it, the less it fits inside the cache, and the cache is expensive, right? So they were very incentivized to make that as small as possible, which meant fewer flags, which meant fewer options, okay? Once you have dep and you've got this, now you must return into a code page, right? You must ROP. You must perform return-oriented programming, which means you have to return into code that already exists. It could be misaligned code that already exists. It could be entire functions like you will do in homework 1. That's a very basic ROP. You just return directly into one function, and you're done, right? Or you can set up a stack frame that basically controls the rest of the program performing all of its functions through code that already exists. Now, if you are owning something like an iPhone, I'll hold one up. That, for the longest time, now it does JIT, but for the longest time, it was not possible to allocate executable writable pages. Like that was part of what they did. And they signed the code pages and they checked the checksums on all the code pages, right? And so when you wrote shellcode, you never jumped into arbitrary code you wrote. It was just a ROP chain, start to finish. Everything you wanted to do had to be done in a ROP chain, okay? But ROP is not hard. ROP is incredibly simple. There are no problems to solve in ROP except for the very first gadget, which we call the pivot, the stack pivot, right? When you have the control of the return address, you get one chance to get control of the stack. Now, if you are doing a stack-based buffer overflow, no problem. You have control of the stack. You will almost never be doing that, right? You will be hitting those heap bugs. You will be hitting a vtable. And so the data that you control lives on the heap, and ESP ain't pointing there. And so you've got one chance to say, at crash time, what registers are there that point at the object that I have used to gain control? Because that's where my data is. Now, I have to find code that will take the value of that register and stick it in ESP, and then it's game on. Everything after that is just typing. It is incredibly simple. You will always find the gadgets you need, except for the pivot. Sometimes the pivot is very hard to find, and sometimes it's really big. So the solver that I have on GitHub has found ARM gadgets, stack pivots, that are multiple calls long, and if I printed them out, they would be like 15 pages of text. And I looked at the thing and I was like, there's no effing way that works. My solver's busted. And I put the return address in, and the shellcode ran. Like, yeah. Right? But it's real hard to find those. You couldn't find them by hand, right? So that's what you would use a solver for. 15 minutes. All right, so 2007 comes around, and people start ending up having to build these ROP chains. But it's not hard. Anyone who got this far in life, this was the easiest part of the solution. Once you get to the ROP chain, you're like, yeah, I'm done now. Now I'm bragging to my friends, so I just got to finish this thing up, right? And so that is what ASLR is meant to defeat. So, 97 for Solar Designer. There's actually a funny email chain on Usenet from 1990, I think it must have been sometime in early 2000, maybe 2002, 2003, when people were like, oh, I invented ROP. And Hedda, the guy who wrote those ABOs, said something clever about how he had been doing it since the year of our Lord 1992 AD. And so that kind of became like an inside joke at Immunity. So we all have 1992 AD tattoos. Or because it is incredibly common that white hats will be like, I invented this thing, and black hats will be like, we've been doing this for 20 years. You have not seen it yet, you know, because you're not solving the problems that we're solving. So you have your stack, and it doesn't matter where you put it, whether it's in the stack or the heap, as long as ESP points there, that's the stack now, right? Wherever ESP is pointing, that's the stack frame, okay? And it's very easy to say, here's my call, here are the call arguments, right? Here's another call, here's another call, here's another call, right? You just build it out of return addresses, but those return addresses don't have to be actual return addresses. They can return into any existing code. They can return directly into functions, right? Like I can say call mprotect is the classic one. The classic way that you would solve the ROP problem is you either reprotect the stack, so you change the page protections on it by calling the mprotect function. So my return address would be the address of the function call, and then the next things on my stack are just the arguments to it. And then I have the return address that goes back to my stack, or it's jump whatever register I've stored off. Now, if I want to get back to my stack, I've changed ESP. I have to have some other register that points back into it, or I can't get there, right? And that's why it is critically important to understand at crash time where are all of my registers pointing, right? You know how when we look at a stack frame, we save off everything we're going to use so that we can pop it back off again, right? Anything you don't save is gone. And so you have to be very careful not to corrupt things that you will need to make this sucker work, right? And you have to be very aware of my ECX is pointing at something I control, but my EDX is pointing back into the stack. So after I do that, if I want to execute code on the stack after my mprotect, I'm going to have to jump to EDX, which means that anything that I do in between can't corrupt EDX. And also, since I'm calling mprotect's probably going to change EDX. I need to store it someplace and then pop it back off later. So sometimes you're adding stuff to a secondary stack of your own, where you are storing off data that you have with pieces of gadgets, right? This is not complicated by itself, but what it is recursive in your brain, right? I'm solving problem A. Solving problem A causes problems B, C, and D, okay? I have to solve problems B, C, and D, okay? So you are building kind of this recursiveness in your own brain, which is why I say learn to use notes, because that is a lot of mental stack to keep up. And the second your partner comes into the room and asks you something obnoxious, all of it goes out of your head and you just throw stuff across the room. It's not good, so use your notes. All right, so we've got these ROP chains. We can solve this problem. It's easy. What's the problem? What are they going to do next? The next thing is address randomization, or ASLR. So on the Linux machine, there's syscontrol. It's VA randomize. Is that right? Something like that? Yeah, so you can turn that on or off. And if the code is compiled as position-independent code and ASLR or VA randomize is on, what happens is every module will get loaded at a random address. What do I mean by module? I mean libraries, .sos or DLLs. I mean the binary itself, the program that's being run, okay? Now, they will be randomized by the whole thing. So all those text pages, they're not split up and put in different places. They're just as they are in the file, but they're put at a different base address, okay? So that means if I can leak the address of one function, say by dumping a vtable somehow, then I can calculate the base address of that module. If I can calculate the base address of that module, then I can do all my ROP. My assumption is always that any library that I can find the base address of has enough gadgets to do ROP, and that has never been wrong so far. Sometimes, very, very rare cases, you can't find a pivot if your reference to your data is extremely oblique. So like if it's, I've had my reference to my data be like, what ECX plus 20 points to is a pointer that points to my data. And that's when the pivot gets weird, right? That's pretty rare. Normally, you hit a vtable, ECX is pointing to the this pointer. The this pointer is pointing at the object you control. Ta-da, you're done, right? So it's usually move ECX, ESP, that's your pivot. And so you can almost always find that. But the idea is, if we can get the vtable pointer from the object to print out, here's a simple way to do that. Let's say we have two objects next to each other. And one of these is a string. And this guy's a class with a vtable. And I can write the string and also have it printed out to the screen. Well, string prints terminate on null pointer, on nulls, right? So what if I just write this sucker right to the edge of the vtable without overwriting it and then ask it to print it out again? It's going to print me my string and then 4 bytes of the vtable. And now I've leaked the vtable out, and then I do math. I open up my disassembler, I say, where is this vtable in memory? Okay, the offset is 4028 from the base address, so whatever thing came out, I subtract 4028, now I have the base address of the module, I can build my whole graph chain, okay? That is what ASLR is meant to do. It is meant to stop you from ROPing, but what it really does is it says, now I need 2 bugs. I need the bug that gets me control in the first place, or the set of bugs that get me control in the first place. I need another bug to get a peak. A peak. Eek? 2 E's. Which is a specific type of info disclosure. A peak is an info disclosure of a pointer inside a code page that you can then use to calculate a base address. Okay? Very specific. Info disclosure can be anything. It could be data from the program. It could be the directory the program's running in. It could be the user of the program. Any of that stuff is info disclosure, right? If you have ever seen like a PHP directory traversal, sometimes those will be called info disclosure. But this is specific to memory corruption exploitation. It means address something in the code page. It can be anything in the code page. It doesn't have to be a vtable, because when you print that out, and you figure out where it is, it's always going to be the same, right? It will always be the same offset from the start. And so that's how you beat ASLR. It is the most expensive mitigation, but if there's no dep, right, if they haven't protected the heap and the stack, ASLR doesn't work, right? It doesn't matter, because you can execute anything. You don't have to ROP. So dep and ASLR are 2 halves of the same mitigation, basically, right? It just took them goddamn forever to get ASLR implemented. And the reason for that is you have to compile the code that's getting ASLR'd in a specific way, position independent, right? A lot of times, if you compile code statically, it will use static addresses rather than relative. Let's use absolute addresses instead of relative addresses. Or it won't store enough information to allow the loader to randomize its base address, right? Anytime that there's an absolute address called, that's got to be stored someplace in a header that says to the loader, you got to go fix all these places up, right, when you set it up. So for many years, even though the loader could do ASLR, anyone who loaded a library that hadn't been compiled very, very recently didn't matter, right? Because you'd be like, oh, all this is ASLR'd except for that one module that's always in the same place that has everything I needed. So it didn't work at all, right?
Is there like a specific port at like the beginning of the binary that says, hey, this is encoded with PIE?
Yes.
Okay.
Yep. And probably you could dump that out with option dash for the headers. And it'll probably say something really oblique rather than position independent. It'll say something else, because that's how object is. So this is kind of showing you what I drew over there, right? writing up to the edge of the V table to get it printed out. This is a really common way to do it, especially in browsers where you've got JavaScript. If you are attacking browsers, you are the luckiest person there is. They're complicated and obnoxious, and they're basically an entire operating system unto themselves. Nowadays, if they are sandboxed, they even have a kernel, basically, right? All the requests that individual process or thread that is rendering make go through this other process through inter-process communication, just like if it were its own kernel. However, you have arbitrary code execution already, right? If you can send JavaScript, you can allocate whatever you want. You can free whatever you want, right? You can cause allocations of a given size to appear or disappear at will. You can do very precise overwrites without having to find primitives. That's what JavaScript in a browser gives you, is basically every primitive on a silver platter that you could possibly want, right? So the next thing that happens here is kind of the rise of use after free bugs, right? And the way that use after free bugs work is a very broad category of bug, but basically what is happening is someone has freed a pointer, and someone else still has a copy of that pointer. We saw a couple times in the libraries how 2 or even more linked lists contain the same pointers to be used in different ways, right? One of those pointers goes away, you've got to fix up all the lists. And if you are in a strange, complicated situation, somebody may have failed to fix up their list. And then if they go use that pointer as though it is valid data still, it could be anything because it has already been freed, it could be given away again. And so that's basically what you are looking to do, is set up a situation where somebody frees something, somebody else holds on to a pointer to it, and you, knowing the size, cause something to be allocated there that you can control. So if you've got JavaScript, you can make a string of that size and have full control of the data. Now, you have a type confusion situation. And a type confusion situation is where the system or the program that's running thinks the memory is of a certain type, right? That it's got variables that make sense, that there are function pointers that make sense. And you have put an object in there of a different type, generally a string because it's the easiest for you to control, but it doesn't have to be. Anything of the right size that will fill the hole will work. And when it treats it like the other object, it will be using data that you have provided in a way that it does not expect to be invalid, okay? The classic way to do this is just to have something that's got a vtable, it's a class, but you put a string there, and since you control the string, you control the vtable pointer, and you're done, basically. You just ask that object to run one of its functions, and that's it. So the way that you would see these constantly was in overloading functions in JavaScript, right? So you would have a some loop that would loop over the elements of an array, and then you would say print that element, but you would overload the print function with your own version, and then the loop, the print function that you overloaded with, would free it or change it, because anytime you change something in JavaScript, it frees the old one and makes a new one. That's just how Java is. And the loop would contain a reference to that data still, but you will have freed it. And so if you do your overloaded function and then another function, you would get a use after free, basically. And there were hundreds and hundreds of those, and finding them is very difficult. You can still find those today. One of the great ways to find that, and what I think would be a great use of LLMs, is that if you look at the V8 repository, you will see that there's a whole bunch of regression tests in there, which are tests that are very small chunks of code that used to be bugs. And so they write these regression tests to say, when you're messing with V8, run all of these scenarios again and make sure you didn't add that bug back in, because it's pretty common. Well, if you feed that as learning data into an LLM and you say mutate these and dump a bunch of shit out, it doesn't matter if the code's invalid or not, right? 99% of the time an LLM can give you absolute garbage code. we want garbage code in this case. As long as it runs on V8, you can run hundreds of thousands of possibly meaningless code snippets until one crashes, and then you got your bug, right? So that's, I mean, basically what a fuzzer does. And a lot of that data is going to be completely invalid, so it doesn't